Hello everyone. So previously we had discussed on the problem stone game 1, right? So today we'll be discussing on the problem this one 110 problem number 1140 stone game 2, right? So let's see what the question states here. Alice and Bob take turns removing the first X piles, right? Alice and the Bob, what they do, they take turns removing the first X piles, right? X greater than or equal to 1 and less than or equal to 2m. They have given, right? 2 million. So, and then set m equals max of m comma x, right? So both play optimally. So again, listen to this carefully. Both play optimally. We have to return the maximum stones Alice can collect starting with m equals 1, right? M equals 1, right? So see, we have been given the piles, which is positive basically, right? All the elements are positive numbers, right? So this is fine. Output that we have got is 10 here. How? See, if Alice takes one pile at the beginning, Bob takes two piles, right? Then Alice takes two piles again, right? See here, Alice will take this one too. Then Bob will take one. Yeah, either of them. Then Alice will take these four, right? These two actually. Alice can take two, right? So this is fine. Alice will take one pile at the beginning. Bob takes two piles. So Bob will take two piles, sorry, not the one. So this Bob will take 7 and 9, suppose. Yeah. 9 and 7 would lead to actually 16. So Alice will take 10 here. So again, Alice will take 2, right? So this would lead to 4, 4 and 2, nothing but the 10 stones in total. So if Alice takes 2 piles at the beginning itself, yeah, at the beginning itself, Alice takes this one, then Bob can take all the 3 piles left, right? So in this case, Alice gets 9 stones in the this one. What do we call in total? So 10 is greater than the 9. Actually, we'll be considering this itself. Yeah. So we will be returning 10 here, not 9. Yep. So we return 10 since it's larger or greater. Yeah, we can just consider the larger one actually. So we return 10 here in this case. Yep. They have clearly mentioned in the explanation. So Alice will consider 2, this one 4, 4. Alice will consider 1. So Bob will consider these two. Then Alice will consider these two. Bob is not left with anything. So Bob stays quiet here. So this one 2, 4, 4. Alice will consider 2, 4, 4, which will lead to 10. So this one will be returning as output. Yeah. So same goes with the second example as well. You can just consider, you can just do it in the same way I showed for the example one. Yep. So this is the question. They have given us wonderful examples just for the sake of understanding. So let me tell you one thing before hopping into the approach part. So we will be solving this one with a 2D dynamic programming or the dynamic programming. We'll be making use of 2D DP. Fine. Yeah. First, what we will do, we will pre-compute the suffix sum, right? We will pre-compute the suffix sums. So suffix of I will be equivalent to total stones from the this one pile. Suffix of I will be this one total stones from pile actually. Total stone from we can consider pile. This is fine. We'll pre-compute suffix sums. We'll pre-compute suffix sums. So suffix of I is equivalent to the total stones from the pile I to the end actually. Pile I to end actually. This is fine. Now, if the player takes X piles, right? Accordingly with the constraint, they have given X greater than or equal to 1 and less than or equal to 2 into M, right? So if the player takes X piles, the opponent then plays from I plus X with a new M that is equivalent to the max of M comma X, right? That will optimally get DP of I plus X into M. Yep. The current player thus secures here. So current player will secure what he can secure here. So this one we can just write it in this way. Suffix of I minus we can write dp of I plus x into m, dp of I plus x into m actually. Yeah, because total remaining is suffix of I. Opponent gets dp, remainder is what current keeps, right? So dp of im is equivalent to the max of x greater than or equal to 1 less than or equal to 2m comma I plus x less than or equal to n, right? So this one we don't have to vary that much, so we'll be seeing this one within the code itself, but base case we will be going with dp of n. I can just write it in this way. dp of n, I'll just represent this one by star actually. dp of n star equals 0 initially, base case. Yeah. So let's try to implement the same thing, whatever we discussed in the form of this one on by considering the example one here, right? So first thing here, we have 27944, right? So total, we'll sum up this one first actually, everything. So 2799 18. So this one will be 22, 26, right? So the sum will be 26 here. Sum will be 26, so we will compute the suffix, right? So we'll compute suffix. When we compute the suffix, actually suffix in the sense we know, right? Prefix and suffix, you know. So we'll compute suffix, so this will lead to 26, 24, you can just count, 17, 8, 4 as well as the 0, 8, 4 as well as the 0. So we will be going with a bottom up approach, right? Via memo. So we will be going with a bottom up approach via memoization, right? So this is fine. First, bottom up approach in the sense, so we'll be going with a reverse iteration for this. We'll be starting with this 4 actually. Yeah, we'll be working bottom up. Yeah, we'll be going with a reverse iteration. First, what we will do, we will consider dp of 4 initially, base case, right? dp of 4 star. So this one will be 4, only one pile. So this one, first one, only one pile, right? So next we will be going with a dp of 3, 1 actually, dp of 3, 1. So here in this case, we will go with max of take 1, nothing but 8 minus 4, that is equivalent to 4, and max of take 2, nothing but 8 minus 0, that is equivalent to 8. So we will be going with max of, basically take 1 we got 4 and take 2 we got 8, 4 comma 8. So max of 4 comma 8, that will lead to 8, right? So this is fine. Next let's go with a dp of a 2, 1 actually. Yeah, we have to go until dp of 0, 1, right? So this will be max of take 1 and take 2. So what will be the max of take 1 here? So this one we will get 17 minus 8, that is equivalent to 9, and 17 minus 4 for the take 2, that is nothing but the 13. So max of 9 and 13 will lead to 13 here. So next what we will do, we will be going with dp of this one 1, 1 actually, dp of 1, 1, and then finally dp of 0, 1, dp of 0, 1. So let me write it over here. So dp of 1, 1 is nothing but max of take 1 and take 2, right? Take 1 is 24 minus 13, nothing but 11, max of 11, as well as this one, what do we call, take 2. So this one will be 24 minus 8, nothing but 16. So we have calculated this one, right? We are going with this actually. Suffix max of this one, 24 minus 8, nothing but the 16, right? So max of 11 and 16 would lead to 16 itself. Finally, dp of 0, 1 is nothing but the max of take 1 and take 2. 26 minus 16, nothing but 10. This one, 10 and 9. 26 minus 17 is nothing but 9. So this one max of 10 comma 9, sorry, 10 comma 9 would lead to this one, what do we call, 10 actually. Yeah, we got 8, 13, 4, 8, 13, 16, and 10 actually. Yeah, so overall at the last cell we got 10 here, right? So this 10, yep. So we will be returning this 10 as output. Actually, we will return this 10 as output. The output that we got here is 10, which is equivalent to the output that they have mentioned for the example 1 within the question. So we'll be going with the output dp of 0, 1 actually. Yeah, in simple terms, we have to return basically dp of this one. Im will be going with this one, right? So that will be seeing in the code, don't worry. So this one, the output that we got here as 10 is equivalent to the output that they have mentioned for the example 1 within the question. So now as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to big O of n square into max factor into max factor, right? So this will be the time complexity because see, more precisely, we can just go with the big of n square into 2, that is bounded by the big of n square. Because for each I of n and each m that is less than or equal to n, we iterate up to 2m, right? Accordingly with the constraints less than or equal to 2n with n less than or equal to 100, right? So this behaves as big of n cube, right? In the worst case, it will be effective, the effective bound is equivalent to the big of n square into n, which is equivalent to the big of n cube, right? So or else we can simply write it in this way, big of n square into max factor as well, right? So let's go with this instead, right? So this is fine. What would be the space complexity? The space complexity would lead to big of n square, as we will be making use of the dp table. um, this one plus big of n for the suffix that we calculated initially, that I showed, right? So we will be making use of the dp table along with the suffix. So concisely we can just go with a big of n square space complexity, right? The time complexity and the space complexity for the code that we'll be writing in the future would be big of n square into max factor and big of n square respectively. Now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the. So first, let's go with the this one. Let's initialize the DP. Just go with private here. Int DP. So this is fine. Next, let's go with the suffix sum array, where suffix of I equals total stones from the I to n. So let's initialize the suffix as well as let's go with a number of piles as well, and nothing but n. So let's initialize these two. So just go with private int suffix as well as private int n. Yep, this is fine. Next, let's go with a this one. So let me do this one outside for a change. Let's consider this one. Just give me a second here. Yep. Now, let's come to the main function here, stone game 2, right? So we have been given, we have considered the parameter piles here. So this is fine. First, what we'll do, we'll initialize n here. So we'll be making use of the length of the piles everywhere. So I'll just go with piles dot length. So this is fine. The next step would be, let's build the suffix sum of length n plus 1 and suffix of n that is equivalent to the 0. I'll just go with suffix equals new int of n plus 1. So this is fine. Next, we will fill the suffix from the end, nothing but suffix of I equals piles of I plus suffix of I plus 1. So let's go with a for loop here. I equals n minus 1, I greater than or equal to 0, I, I'll just give here minus. So within the for loop, what shall I do? I'll just give suffix of I equals piles of I plus suffix of I plus 1. This is fine. So let me come out of this one entirely. So let's go with the DP dimensions then, but n into n plus 1, since m can grow up to n, we know this one, right? So this one, let me assign this one to new int of size actually n into n plus 1. So this one we have to write this one within the array, right? N size n plus 1. Now let's do one thing. Let's initialize the DP with minus 1, meaning here not computed yet or not calculated yet. Let's go with this one. Two for loops as usual. So this one will be int I equals 0, I less than n plus plus I. So one more for loop here for int j equals 0, j less than or equal to n actually plus plus j. So this is also fine. Yep. Now next we'll be going with the dp of ij. So we'll be going with the dp of ij that is equivalent to minus 1. So this is fine. So let me come out of this one entirely. Now so why this much of Capman here? So yeah. Let me consider here, we have to start the DFS from index 0 to n minus 1, right? So we haven't written to perform the DFS, we have to write the DFS function first. Yep. So that we haven't written that one yet actually. Yep. So let's do one thing. Mm, so here I have written dp of ij. This is fine. Yeah, let's do one thing. Let's write the this one. What do we call DFS helper method first? Then we can just make use of the DFS within the main function stone game 2, right? So DFS, why DFS here? Because it returns the maximum stones current player can obtain starting at the index I, right? So let's try writing the DFS function. I'll just give a private in DFS of two parameters int I int m. So this is fine. So within this helper method DFS, if we have consumed all files, then there is nothing to take. So this one, if I greater than or equal to n, then we have to return 0. Then we have to return 0. If already computed, then we have to return the memoized value. So I'll just write one more if condition here. If dp of im, if dp of im not equal to -1, then we have to return dp of I and m, dp of I and m respectively. So next, let's go with the maximum stones that we can obtain from here, right? So let me go with best equals 0. This is fine. We can take x files where x is greater than or equal to 1 and less than or equal to 2 into m. So that's what they have given the constraints, but not beyond this one array end, right? For each possible choice x that we have considered or that we consider, opponent will play from I plus x with m, right? So that is equivalent to the max of m comma x. We know this one from the question. So let me move on. Let's move on with the iteration part. So this one will be for I can just write it in this way: x equals 1, x less than or equal to 2 into m, and this one I plus x less than or equal to n plus plus. So this is fine. So within the for loop, opponent's best actually from the remaining is equivalent to the DFS of I plus x comma max of m comma x, right? So I'll just give your int opponent equals DFS of I plus x, this is fine, comma mat dot max of m comma, this is fine as well. Next, let's go with the current gain, that is equivalent to suffix of I minus opponent. So this is fine, man. Yep. The next step is we have to maximize over choices. So this one will be if, let me go with the current gain. If current gain, if it is greater than the best, then best equals current gain, right? So this is fine. Fine, let me come out of this one. So we have to memoize and return nothing but here dp of im. Let me assign this one to the best. Along with it, let's return the best. We have to return the best itself, right? So I'll just return the best here. So this is it for the code. So this is it for the DFS helper method, right? So we have to make use of the DFS helper method within the main functions stone game 2, right? So that's the only thing that is left actually. So let's do one thing. Let's start from the index 0, meaning DFS. Let's perform the DFS from the index 0 with m equals initially 1, right? So I'll just go with return. So let me paste the DFS here, helper method that we have written. This will be 0, 1. Yeah, so this is it for the code. So let me hit the run button. Formatted the code and let me hit the run button. We have some errors here. So this has to be multiplication. This thing I believe. X equals 1. What we did there? Yeah, x equals 1. X less than or equal to 2 into m, right? So this has become 2 into m. Yeah. So let me hit the run button now. Yeah, the sample test cases are getting passed. So let me hit the submit button quickly. I can clearly see here, man. All the test cases are getting passed. Means whatever the code that we have written works perfect for all the test cases. Yeah. So I hope the solution part is completely clear. along with the approach and the complexities. For now, this is it. Thanks for watching, guys.